Welcome back. So now Erez Nesharim from the Technion, Israel Institute of Technology, will continue his lecture series on bounded orbits for diagonal flows on the space of lattices.
Thank you for the introduction, and thank you again for the opportunity to speak here in this very exciting occasion. And thank you for your questions yesterday. If you have more questions, please ask during the talk. So one of the questions was what I'm about to do today. So today I want to prove the same theorem we proved yesterday, the theorem of Schmidt or McMullen that badly approximable numbers is an absolute winning set. But I want to do it in a different method, in a way that will not use the what's so-called simplex lemma, this easy statement, but that there is only one rational point that is dangerous, that is that Alice needs to avoid in order to win the game. So I will do it again without using this statement, because that is the statement that is difficult, not easy to generalize to other situations. So let me start with the correction of yesterday's constant. So we had two conditions in the proof popping out about the constants. One was beta smaller than that. That was to get this contradiction to get the simplex lemma, to get the claim. And we had the second condition that the constant over q squared is smaller than beta to the power n plus 1 r0. That condition was in order to make sure that in Alice's next turn, she can remove this one particular unique rational point. So that was and that particular denominator satisfied this inequality. So this is implied by this. So yesterday I think we had not C equals R0. But the rest is okay. So just make sure that R0 is smaller than beta over 4, and that the constant is beta times R. Okay, so maybe let me state again. Go in a somewhat chronological order to the over the over what was proved during the years. So we finished with okay. So Schmidt in 69 proved that BA is winning for every M and N. So the general case of matrices, and then the question was let me say that Schmidt raised a conjecture. It's conjecture about what happens for different weights. So that was on the board yesterday. So BA for every W1, W, and W prime two-dimensional weights. So I'll soon define this again. What is the weight? BA W intersection with BA W prime is not n. So okay, so let me define this these sets in general. So given a vector, a probability vector, well, a vector W in R. So it's an m plus n. It's a vector with m plus n coordinates, such that the sum of the coordinates is 0. And I'm assuming that they appear in decreasing order. Otherwise, we can permute. And I'm assuming that W1 is bigger than WM, which is bigger than 0, and all the rest, WM plus 1, are bigger than WM plus n. Okay, and now there is a similar definition of what it means to be badly approximable. So X in M and R is badly approximable well with this weight W. So let's call it W badly approximable. If let me write it this way. So if there exists a constant such that X times Q, such as for every P in Zn, and Q in Zn, not 0. This system of inequalities, X times Q raised to the let me write it this way, W plus times the weight of the vector, 1 over minus W minus, is bigger than this constant. And with this notation, I mean that so here there is a vector, a vector with m coordinates, and I raise it to the power 1 over W1, Wi. So the ith coordinate, well, in general, for Y in RK, and the okay, this raising it to the and the W some vector in RK, or positive, Y to the W is the maximum over the coordinates of Y to the power WI. Okay. Hopefully this is meaningful. It just means that I can write it in coordinates. I can just write it in coordinates. So for every I, if you take the ith coordinate of this vector, which is the ith row of x times e times q plus pi. You raise it to the power 1 over wi, and you multiply it by q for every I and for every j, by q to the qj to the power 1 over minus w m plus j. And you want this to be bigger than this constant. Not for every, just that there exists. This is the supplement. This is the maximum overall coordinates. Okay, this is a complicated way to write something that's natural. Let me write it again using the Dani correspondence. So this just means that if you define this matrix AW to be this diagonal matrix e to the minus e to the w1 c e to the w m c, and here you put e to the minus w e to the plus. Okay, just put it the diagonal. On the diagonal, you put this weighted vector, and you define this ux like we had yesterday. So this is this unipotent element with x on the right corner. Then that was so this is the Dani correspondence. The Dani correspondence, or an instance of Dani correspondence is the following. Which was proved by, in a similar way that we proved yesterday by Kleinbock. I put here 96. Says that this orbit, so x is W badly approximable if and only if this orbit is bounded. So A W T this way, A W T A W U X, this lattice is bounded as t goes to infinity. Is bound. So let's go back to the Schmidt's conjecture. So okay, so it just says that drawing a picture that was here yesterday. So we have those two different, or not necessarily different, but let's say they are different weight vectors. So it means that you are looking at diagonal elements of this form. So you look at yes, two different diagonal elements. So e to the W1, e to the W2, the minus t, and the same with the prime. Okay. And you are asking if there are bounded orbits, if there are orbits, if there are so are there? Is there? Does there exist? Does there exist? X. Well, here in this case, it's just a vector. X1, X2. Such that right here. Sorry about this. AW UX are bounded. So, okay, so yes. The third line, okay, is the I call it the weight space, and usually I assume that the weights are sum up to 1. So yes, this is. I mean, otherwise you can rescale. So in case these W1, W2 are positive, then up to scaling, weights are look like this. So this is the third line, and you look on orbits along this to one-dimensional, one parameter flows. X. Okay, here you can, yeah, this is just this vector. So then, okay, this was a slight jump in the order of the way things were in the chronological order. So I was mentioning, just because I wanted to mention Schmidt's conjecture, because I think this already raises the question about what happens in different Lie groups, or so. In different Lie groups, and well, here Schmidt conjecture is still about the space of lattices, but it already involves different one-parameter flows. So now this question can arise, can become in a great. You can ask this question in greater generality. So Dani, for example, proved. So and okay, yeah, Dani proved in '86 that for any G semi-simple, connected Lie group with R rank 1, with R rank 1, gamma a lattice in G, a lattice. GT, a flow, a one parameter flow, one parameter flow. With okay, with at least one eigenvalue that is not one, so in absolute value. So with the AG having an eigenvalue bigger than one in absolute value. Then the dimension of the set of bounded orbits, or G gamma, such that G, G, G gamma is bounded. Equals the dimension of G. So there are two main assumptions here. One of them is that the rank is one. So it's not about the situation with the higher rank it's similar to the case where m equals n equals 0. And the other assumption is obviously is this. Well, which says that we are in the situation of an expanding flow. Okay. Yes, this is true in general. This was proved. This was conjectured by Margulis in the 90s in his 1990 paper, and then it was proved by Kleinbock Margolis in 96. So maybe I don't have to write this.
It doesn't follow from cell length.
Yes. Okay. So yeah. So maybe I'll write this. So Kleinbock Margolis. In 96, solved a conjecture of Margulis and proved that this is true in general. So maybe under a slightly more restrictive. So gamma is a lattice in a Lie group, and GT is a diagonalizable. Then again, this is true. So the dimension of bounded orbits. Is the dimension of G. And this led Kleinbock to conjecture. So Kleinbock conjectured. That something more should be true. That it really should be winning. So okay. So after Schmidt invented the game, it's basically absent. Well, it's basically, it took some 20 years until Dani, it was basically forgotten by the community, at least by the written community, and then Dani proved his result using Schmidt's game. And after Kleinbock and Margulis proved this general statement, Kleinbock conjectured that at least for the case of SLN, so let me tell you that bed BAW is winning. So that was maybe not a conjecture, but just Kleinbock's problem. Which raised in 96. BW, is it true that BW is winning? Okay. Okay, that was, so absolutely winning is not true in general, because in higher dimension you need you need to avoid to avoid hyperplanes instead of avoiding neighborhoods of lines. So that was more or less the next. Okay, at that point, I think it was not even clear if this set had a full dimension, because there is a slight difference between saying something about the set of bounded orbits and saying something about the set of just what happens to those matrices, those specific elements that look like UX in the group. So that led to a series of works. So let me just mention some names: Pollington, Dani, in 2002, proved that the dimension of bed W is n times n, or okay, for n equals 1. You need this condition. You're saying about this condition? Yeah. Okay. If it's diagonalizable, then if it doesn't have an eigenvalue that is not greater than 1, then it doesn't have an eigenvalue which is not 1. Then it just all the orbits are bounded. So just an empty assumption. You don't need the assumption. But sure, this is the more interesting case. Okay, then there was Okay, there I didn't assume that that it's diagonalizable. Maybe it's not necessary to assume this, but this is the way it's stated in Dani's paper. So. Okay, so let me just mention. So then there was a work by Kleinbock and Weiss. So let me mention the important landmarks in 09, where they proved that generalize this for every n, for every m and n. And there was some kind of a competition between people from the Oppenheim approximation and people who are using dynamics, trying to maybe prove Schmidt's conjecture until. Okay, and this is what led to a series of other works. So let me just mention this work by Broderick, Fishman, Kleinbock, Reich, and Weiss in 2011, where they actually invented, well, following McMullen's absolute game, they invented another game. So maybe let me define it. So let me briefly recall Schmidt games. We had this Schmidt game. Was at step 0. Okay, before the game starts, there was 2 parameters, alpha and beta. And at step 0, Bob chooses a ball. Step n+1, Alice chooses a ball inside Bn, and Bob chooses a ball inside n+1. And then there is the outcome of the game. So the outcome is just the intersection. Then there was the absolute game, McMullen. Where having a different color. Where before the game there is nothing, and then Bob chooses a beta. Is this visible? Yes. Bob chooses a parameter beta and B0. Alice chooses a ball, and then Bob chooses a ball which do not intersect AN. And then there is the hyperplane game. hyperplane game. Hyperplane absolute game. Where, again, Bob chooses a beta between 0 and 1 and a ball. And Alice chooses now a hyperplane. So Alice chooses the neighborhood of a hyperplane, which is B, the neighborhood of some hyperplane. With a neighborhood of size beta times Rn. And Bob avoids this hyperplane. So he chooses a ball which avoids the An+. Okay, so maybe I can draw this. So that is B0. Okay, so in contrast to the other games, this game is played in the Euclidean space. So there is a neighborhood of hyperplane, and then Bob chooses a ball which doesn't intersect it. One. Alice chooses another neighborhood of hyperplane, and so on. Okay, so the reason this game was invented is because there are obvious obstructions to being badly approximable in higher dimensions. So, for example, if you just look in R2 and you fix your favorite rational line, let's say the y-axis, then no point here is badly approximable. So all the points that look like 0y for every y, 0y is not badly approximable. The reason is that the approximations to this vector is actually the approximations to y. So you can approximate that vector very well. As you can approximate y. So in order of magnitude that goes like a constant over 1 over the denominator squared and not 1 over the denominator to the power 1 plus half. Okay, and then all these efforts were not achieving the ultimate goal. But okay, so in that paper, it was proved that bad BA is hyperplane absolute finite. Okay, let me write it. Hyperplane absolute meaning. Which I'll denote by how. But only for the weighted case, only for the unweighted case. So for if I don't write here, then I mean the equal weights case where is okay. This was just for n equals 1. For n equals 1, and W being the equal weights vector. And this was generalized by Broderick, Fishman, and Simmons. Broderick, Fishman, and Simmons in 2013 generalized this. Generalized to general to every MNN. So prove this result for matrices. That badly approximable matrices with for every MNN with the equal weights. So with the weight vector that looks like 1 over m to 1 over n, minus 1 over n to minus 1 over n. That is a hyperplane absolute meaning set. And this was more or less the state of the art until the breakthrough. So until finally Badzihin, Pollington, Dani proved the Schmidt's conjecture. So B Badzihin, Pollington, Dani in 2011 proved the Schmidt's conjecture. Schmidt's conjecture. And then Badzihin and Dani. Okay, so this opened the door to many new results in increasing order of difficulty. But most notably, immediately after that, they solved Davenport's problem. Which was to just even find the uncountably many points, badly approximable points on the parabola, on the two-dimensional parabola. Okay, this opened the door to many other works. So okay, so as I mentioned yesterday, this was approximately the point where I started my PhD. And I was just, I tried to understand those proofs. And there were many things coming afterwards. So maybe I'll just mention a few of them. Maybe I'll just mention by names. So Jinpeng. And he proved in two papers. So in 2013, in two papers, he proved that that was actually a winning set. So 2013. Let me write it. Bed W1, W2 minus 1 is winning. And then this was improved by myself and Simmons to absolute winning, to hyperplane absolute winning. And then Jinpeng's paper was generalized to higher dimensions, but so Guan and Yu in 2017. They proved it for the case where W1 equals W m minus 1, which possibly can be not equal to the last one, so Wm, and this is bigger than m minus 1. So that is the last one. But most notably, they couldn't do it. So that was, they managed to understand the proof well enough in order to improve, to generalize it to a higher dimensional situation, but where there are just two different expansion rates. Okay. Then finally, An Guan Kleinbock. I should call him Jinpeng An. So An Guan Kleinbock in 2015. They actually so they proved it for a general proved Kleinbock's conjecture. So proved that AWT of G in SL3R modulo SL3Z, where T is bigger than 0. And that's at all those G. All those G such that this is bounded. Bounded. Is hyperplane absolutely. Okay, so here there is a nice property of the Howe property of being hyperplane absolute meaning that it's actually preserved by diffeomorphisms. So you can play this on manifolds. So finally, this was the one more step towards a general conjecture, and then they made the conjecture and conjectured that this is true in general. That this is true for every add diagonalizable flow on every G mod gamma. And since then, there were a couple of other works towards this conjecture. So let me just mention An, Ghosh, and Ghosh, Guan, and Twili, who proved it for true for. Okay, so this was the conjecture. So AGK is true for products of SLN, products of SL2, SL2R. And then recently, Savant was here, and Savant generalized it to, well, proved it in the case of SL2, products of SL2C. Okay. Finally, this is what I wanted to say about reviewing the progress, at least so far. So what was this breakthrough about? What was the main ingredient in the proof of Schmidt's conjecture in the work of Badzihin, Pollington, Delan? So that, in fact, it was not realized at that point. But what they did is they invented another game, which is going to be useful for what I want to do. So let me define this game. So this was realized only a couple of years later, that the techniques they were using were actually the same as showing that something was winning for that game. And nowadays it's called the epsilon, well, the counter game. So what is the game? Again, there is a parameter. So there is some, let's call it alpha, between 0 and, which can be actually 0, and some number. And then Bob chooses again a radius, a shrinking rate, and a ball. And Alice now, she's not choosing a particular ball, but she's choosing actually a collection of beta to the minus alpha balls of radius beta times the previous radius. And then Bob tries to avoid all of them. So Bob chooses some ball, which is in Bn minus this collection. Let me draw this picture. So now this is B0, and Alice can choose several balls, but maybe not all of them. And then Bob chooses a ball inside this, and Alice again chooses some balls inside it, and Bob avoids all of them. Where the point is that, yes, if this alpha is smaller than the dimension of the space, then this leaves enough room for the set, for the set S. If S was a winning set for that game, then if alpha was smaller than the dimension of the game, the dimension of the space, then the set was the winning set will be large. So, okay, so actually, if alpha equals 0, then this is, okay, maybe let me say this somewhere else. If alpha equals 0, then this is just the absolute game. So 0 counter game, 0 counter winning, or 0 counter game is just the same as the absolute game. So any questions about the game, the definition of the game? Or is it clear enough? Okay, so now let me try to use this game. But first, let me give you a characterization of winning sets for this game. So theorem. Okay, so this theorem was actually proved by one direction. Okay, so let me state the theorem first. So S is alpha. I need the definition first. So definition. A set K in some metric space X is alpha diffuse if so the definition is meant to complement the definition of the game, in the sense that if you play the game on an alpha diffuse set, then the game will not stop. So remember that the absolute game can stop if there is no such ball. If by chance Alice erased everything. So if there are if there exists some beta such that an R0 such that for every for every radius which is smaller than R0 and every point in the space in K, you look on there exists beta to the minus alpha. Well, there exists some collection of points. Let's call it Y, a subset of what am I saying? For every set of points, with the number of points smaller than or equal to R to the alpha, beta to the minus alpha. There is another ball in the space. So maybe this should be okay. So there exists a point Z in K such that the ball of radius beta times R around Z is not doesn't intersect, so it's contained in this previous ball beta times the big ball minus all those balls with centers in Y. So let me draw the picture. Let's say this was our X, and there is some subset, some subset K, and X is some point in K, and you take a big ball inside around this X. Then for any beta, for any Okay, the centers of the balls, they don't have to be actually K. So for any set of beta to the minus alpha balls, there is still one more ball inside K, centered at Z, that doesn't intersect the yellow balls. Okay. So this is the game. And so this is the definition. And now the theorem is that S is Cantor winning, is alpha Cantor winning. If and only if, okay, so let me state it, if and only if it intersects every diffuse set. So if and only if S intersection K is not empty for any K diffuse, okay, which is also closed and non-empty. Sometimes this is already included in the definition of alpha diffuse. So, okay, so this theorem, in the case of alpha equals 0, okay, I need another condition. S should be Borel set. S should be Borel set. Otherwise, this cannot be. This is one of the directions. This is not a Borel set. Okay, so I wanted to show the proof actually of that theorem, but maybe I will not have time for that. So maybe I'll just say it. So, okay, maybe I'll just also say that in the case alpha equals 0, and this direction, that was actually one of the motivations behind the BFKRW paper, BFKRW. Was proved by, was shown. So that was one of the motivations of introducing this game, actually, to show, in order to show that winning sets for this game actually intersect fractal sets. So what about the proof of this theorem? So one direction is quite easy. So I mean, this direction is just follows from the definition. So maybe I'll say it. This direction. So what do we want to show? We want to show that S intersects K. So we want to construct a point in the intersection, right? So and what do we know? We know that S is winning. So if since S is winning, there is we can fix a winning strategy, a winning strategy for Alice. So a winning strategy is just a list of instructions to Alice to what should she do whenever Bob is making a move. So no matter what Bob is doing. So in particular, now I want to show that she can use her strategy in order to find a point in K. So in particular, K is diffuse. K is diffuse, is alpha diffuse. So there exists some beta, right? There exists some beta in R0. And also it's not empty. K is not empty. So there exists some point in K. So imagine now that that was the first move of the game. That was the first Bob's move, right? So imagine B0 is B X. Let me call this X0. X0, R0. And beta are Bob's first move. So Alice can make a move. Alice can choose according to a strategy. She can choose beta to the minus alpha. Okay, here. Beta to the minus alpha balls in the space X in order to make sure that in the end she'll find a point in the set S. So let her choose that and then apply the definition of being alpha diffuse. So there is still a possibility for Bob. So the game doesn't stop, right? So there exists this Z, and then so Alice. So there exists this collection of points A1, and then smaller with the number of points in A1 smaller than beta to the minus alpha, and then by the alpha diffuse property, this means that there exists some x1 in K which doesn't intersect the balls in A1. So let this be the second move of Bob, the first move of Bob, and then Alice can still make a choice in the for this ball so B1 will be Bx1 beta times R1 beta times R0, and the game goes on this way to produce a sequence of balls, and then this sequence of balls will intersect. The intersection will be both in S and in K. So it will be in S because Alice used the winning strategy, and it will be in K because K is closed. And those balls are shrinking balls with centers in K. Okay. The other direction is so for this direction, no Borel assumption is needed. For the other, no Borel assumption. On S. I don't have to assume this. Yeah, I'm not assuming this also in the game. Z is in K. Z in the definition of the game. I guess this was not. Maybe was not apparent. Z is in K. I mean, Z is in K. Yes, this is important. trying to prove that if S is alpha counterweighing, then it intersects every K. Yes. The other direction is where I'm trying to construct diffuse set which doesn't intersect K. Yes. And this would be using a winning strategy actually. So this is where I'm going to use the Borel assumption. I'm going to use, it's needed in order to make sure that the game is determined. So if the contrary happens, so if there is no winning strategy for Alice, then if S is Borel, then it means that there exists a winning strategy for Bob. And then you can use this winning strategy for Bob in order to construct an alpha diffuse set which doesn't intersect S. Okay, now how much time do I have? 15 minutes? What I want to do next is I want to go back to our story and prove that the set of badly approximable numbers is alpha diffuse, alpha winning, alpha counter winning for some alpha. And you can say for some alpha strictly bigger than 0 actually. Right? So we already know this. We already know this with alpha equals 0. But what I'm trying to say is that the proof, there is a nice proof that's not using anything but quantitative non-divergence. So let me try and do that and see how much time will it take us. So theorem. I think it will be BA is 1/2 Cantor. Which we already know that it's 0 Cantor winning, so we know more, but ignore this for a second. So we're going to use Dani's correspondence again. So what we are trying to do, we are trying to show something. What is BA? This is BA is the set, the intersection over all epsilon of this set. A, N, U, X. X a real number such that A, N, U, X is not in K epsilon. Or there exists, okay, union. Union over for every N positive. Okay. So assume Bn. Okay, now it's not a good thing. So let me call this T. Assume Bn was assume Bob chose beta and R0, and assume that we are in the end step of the game from Bn was Bt was chosen. I want to make sure that in the next, okay, so I'm trying to show that I'm staying bounded. So I'm staying, sorry, this is inside K epsilon. So this is the picture, right? This is the space of unimodular lattices, unimodular two-dimensional lattices. And this is K epsilon. These are a growing collection of compact sets that exhaust the space, and you're bounded if and only if you stay inside one of those compact sets. And now I want to make sure that I have a large set of parameters for which this remains compact, remain in the compact part. So what do I need to do? I need an estimate what? It is okay. This is one of the main points of the main technical points. But let me say that I want an estimate on the set of points x in okay, this is not BT, on the set of points in BT such that AT plus 1 UX is not in K epsilon. So let's assume that was chosen such that it satisfies this property until time t. So such that for every t, for every I don't know t prime smaller than t, a t prime u x is actually inside K epsilon for every x in t prime. Okay, what am I doing here? And this is going back to Barak's comment. I'm going to fix a rate. So after Bob chooses these parameters, Alice can still choose epsilon and can still choose a rate in which she's traveling along the one parameter flow that I'm traveling on. So and then what she will try to do is she will try to make sure that when along these jumps in this one parameter flow, at least along these jumps, well, constant in time it will be constant jumps. The orbit remains in this compact set that she defined. So she can choose epsilon such that she can choose epsilon and the rate. So actually, Alice can choose. Okay. So choose this parameter b, which would be beta to the minus b squared will be beta to the minus half. Let me go back to white. So choose, or maybe continuing the previous row. So where t is this one parameter flow b, where b beta to the minus half, at is now b to the t, b to the minus t. And what else? Epsilon will turn out to be beta. Beta times 1 over R0. So, okay, we'll figure this out maybe later. With this. Okay, so we need a measure estimate. We need actually a measure estimate. Well, we need an estimate on the number of balls of radius beta to the power radius beta to the power t plus 1 times R0, which are needed in order to cover this set. This is what we need. And okay, so here, and we will get this estimate by first having a measure estimate. So just a measure estimate on this set. But what is this set? I mean, this set is if we can open this up and see that this set is just those parameters x for which there are good approximations by rationals, right? So this set is by rationals in a certain range. So the denominator is going to be bounded by b to the power t plus 1 times epsilon. And these kinds of measure estimates are very common in the Aravinda approximation. But we are going to use just one of the most uniform estimates that exist, which is very easy to explain in one dimension. So when is what are the reasons for this lattice to not be in K epsilon? The reasons are that there is a short vector. And what does AT is doing? Okay, so the key equality to write here is that, okay, assume that there exists some V, such that there exists some V, and let's say V in Z2, non-zero, and some X in BH, BT. and some such that a t plus 1 ux v is an absolute value smaller than epsilon. Okay. Now I want to, so this is some particular point in X, and some particular reason to be, for this X to be not in the bounded part, not in K epsilon. So now I want to see how this vector changes when I change X. Okay? And see how much this vector affects this, the measure estimate. So in order to do that, it's very, it's common to write this as this is actually a long unipotent. So a t plus 1 x equals, so maybe I can write x equals all this x tilde. And let me write x equals x tilde plus x prime. So I can write this as a t plus 1 u x prime a t plus 1 inverse a t plus 1 u x tilde times v. And this I call v prime, and this is actually what happens to a unipotent element when it's conjugated by a diagonal element. So this is u and b to the power 2 t plus 1 t plus 1 okay, so when x prime with x prime smaller than beta to the power t r0, right? Or maybe 2 times that. So this was bt, this was bt, and there was some point here x tilde, for which there is a short vector. Then all the points in bt, I can write them as x tilde plus x prime, with x prime which is smaller than the length of the interval. And now what do I have here? I have here a short vector and applied on it a very long unipotent. Well, I'm saying long because it's about the length of b squared, because beta to the power t is cancelled with beta to the power b to the power 2t, and I'm left with b squared. So it's a long unipotent, long piece of unipotent. So what is it doing to v? It just shears it. So y when it's applied to v, it's just this vector v1 plus y v2 comma v2. Okay. So actually, the length of it is just a linear function. So if it was smaller than epsilon, but it doesn't remain too small for the whole time, then it's just a linear function, and say it's not staying below 1 somewhere. then the ratio of the time that it can spend in smaller than that it can spend below epsilon is limited. Well, it's basically this measure of the whole interval divided by the ratio is exactly epsilon, really. So given that it goes beyond 1, then the ratio of the time that it can spend below epsilon is exactly epsilon. If it went over 1. So this is exactly what we are going to use. Where is the long? The long is this. And so can I take 5 more minutes? Yeah. So. So let's see if we can apply this theorem. So I want to say that the measure, the Lebesgue measure of this set X in B T, such that A T plus 1 UX is not in K epsilon. I want to say that this is smaller than 1. This measure estimate that we just agree upon, which is 2 epsilon times the measure of the ball. Because, okay, I didn't say it, but it doesn't matter if this was the specific vector V that I started with, or any other vector, as long as there cannot be more than 1 vector at a time. So there cannot be more than 1 short vector at a time. So the ratio will be the measure of this bed set will be this ratio, given if, as long as every vector V in Z2 non-zero has a point where it goes beyond, its norm goes beyond 1. So A T plus 1, U X, there exists some point in. So, okay, so let me just take the supremum norm over X in PT of that, of the norm of this vector is bigger than 1. But let's see when is it not the case. So I'm claiming that this is the case. This is the case because BT was not arbitrary. BT was an interval without short vectors. Was an interval for which all the points are in the compact part. So we already calculated this. We calculated this. This is that. So this is this. I'm going to go here. So that's B prime. So that's A n plus 1 A UX of V. Here I should put instead of Y should put here this b get to t plus 1 and x prime b1. Fine. So since this is long, so this means that v2 prime must be if this was smaller than epsilon, if so the negation of star, right? This is star. This was if this remained smaller than 1 for the whole interval, it means that v2 prime is actually must be smaller than b to the minus 2 1 over R0. Because I can apply this. That's just a linear line, a linear function. So if it remains small, then for a long time, then the slope must be small. It remains smaller than 1 for a long interval, then the slope must be small, and it's this. So now I can go back. So this means that I can go back here to see what was v prime. So v prime was that. So it means that a t plus 1 u x tilde v. You know, it's in this box. It's in the box where you put here a 1 by 1 at this interval 1 minus 1 minus 1 1 and this number b to the minus 2 1 over R0. So if I go back once with the right, so the coordinates, so the coordinate, this coordinate is very, what am I doing? This coordinate is very small, and this coordinate is roughly 1. So I can go back once with the flow A, because A was expanding the first coordinate and decreasing the second coordinate. So I can go back once to get that. This implies that at u x tilde is in k b to the minus 1 over R0 in k epsilon, which is a contradiction because I'm assuming that there are no points in BT. That set is not in this. It has a short vector. Okay, so this is the measure estimate. This is the main point, and now using this measure estimate, the main point somehow is that this epsilon depends on is related to beta. It's square root of beta. So it means it's not a fixed proportion of the interval. It's an actual power saving. So it's an actual power saving which allows to prove counterweighing. We'll go back to this point in the next hour.
Okay, thank you very much for the lecture. Are there further comments or questions?
It's just the only thing I have, right? It's not empty. So there is a point, and I can do this. Alice can win. So yes. So the point is that Alice can win no matter what Bob does. So let's just say that he does this. This is just an arbitrary choice, but at least I know that there is one choice, one legitimate choice, because K is not empty. So, and once the game once he chooses that, then already Alice can apply the winning strategy, and the game doesn't stop. Yes. 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 Okay, this is the main point of the proof, right? No matter what he does, Alice can win. So it doesn't matter what he does as long as he keeps playing somehow. For that proof. Okay, so this is the main power of this winning property, right? It says that no matter what Bob does, Alice can win.
So the first one is fine. It can be anything.
Maybe we can talk about this.
Okay, are there further questions or comments? If not, then let's thank the speaker again.